Hi, folks. Welcome to Chapter 2. This is a really important chapter because its focus is on helping you discern what is valuable in terms of information out there and what is not so valuable, and how we in the scientific community think about the sources of information around us that relates to nutrition and health. So, what you can see here is what we'll be covering in Chapter 2 using some interesting examples. And just keep in mind as we talk about the scientific method and various study examples that this is broadly similar across all scientific disciplines. So whether you go on to study chemistry or biology, physics, anthropology, etc., the basic principles of the scientific method will be the same. Approximately 100 years ago, the disease pellagra was devastating communities, especially those in the South and among poorer populations. You could perhaps think of it as the COVID of its time, except that the period of the disease prevalence was measured in decades, not years. At the time, public health infrastructure was modest, so there were not many resources that had been directed at investigating pellagra. But it was commonly thought that pellagra was an infectious disease since it was most often found where people lived close together, particularly prisons and orphanages. A New York doctor, Dr. Goldberger, spent years investigating pellagra and found that the staff of the prisons and orphanages did not develop pellagra, so he ruled out infectious disease. It would make sense that if it's an infectious disease, a prison guard or a nurse at an orphanage that would be in close contact with the people that had pellagra would then develop it, right? He also noticed that the diets between these groups were very different. So the prisoners and the orphans ate a diet that had little meat, dairy, or fresh vegetables, and the staff ate a more varied and complete diet. So he developed a hypothesis that it's likely that diet plays a role in the development of pellagra. Goldberger designed several studies, one in which he was able to give pellagra to people who did not have pellagra previously via feeding them a nutrient-poor diet, and one in which he had pellagra patients eat a nutrient-rich diet and their pellagra disappeared. So he came at it from both sides of the possibilities. Dr. Goldberger also tested the infectious theory by exposing a group of people who did not have pellagra to excretions from those who did have pellagra. So if it had been infectious, you'd think that would be a sure way to prove it. But no one got pellagra from being exposed from the excretions. Despite coming up with convincing evidence, Goldberger's work continued to be rejected by the public. Sometimes the public just isn't ready to accept the science, and as well the scientific community at the time was also not quite ready for Dr. Goldberger's findings. Sometimes it's hard to change long-held beliefs and perceptions, but that is one of the most important roles of science. So even though Dr. Goldberger's work was controversial at the time, later researchers were influenced by his work and they were able to use his studies to help formulate further theories on nutrient deficiencies and disease, which of course is now a widely accepted fact in nutrition, that these two are often connected. And of course, the vitamin niacin, or B3, was found to be the specific nutrient whose deficiency creates pellagra. Prior to the modern era, society's nutrition information was curated over centuries, even thousands of years, passed down through the generations. Many of these traditional perspectives on nutrition do remain valuable. However, there is also a fair amount of incorrect information. And as our diets and lifestyles have changed greatly over the past few hundred years, and the amount of misinformation has increased, as well as the incentives for creating misleading nutrition information. For instance, the biased information that can sometimes come from businesses that sell food, beverages, and supplements. We need to have a more formal, unbiased system for giving nutrition advice to the public. So, given these challenges, we benefit from having our government have dietary recommendations that are drawn from decades of research that was conducted using the standardized scientific method. So let's break down the scientific method using the example we discussed here. So in step 1, Dr. Goldberger made observations about pellagra, the conditions and diets of both those who had the disease and those who did not. Step 2, he formulated a hypothesis around the possibility that lack of a well-rounded diet created the disease. Step 3, he did a review, likely, of at least a few of the prevailing theories of the day, but as there was not a lot of information at the time, it was still early in the realm of public health, we can say step 3 is a lot more vigorous these days than it was 100 years ago. Step 4, he designed a study to test his hypothesis, giving a nutrient-poor diet to prisoners in order to induce pellagra, which in fact did happen. The data was analyzed in step 5, for instance, how many of the prisoners developed the disease versus how many did not. And as it turned out, it was quite a large number that developed it, so he could look at the data and say this is fairly conclusive. The results are published in step 6, and then step 7, peers and the public responded, for instance, in this case with a lot of criticism. So more studies were conducted specifically around disproving the infectious disease theory of pellagra. Scientists are trained to be keen observers of the world. They look for patterns, connections, correlations, and they ask questions. They think and they research, and then they develop a hypothesis, which is essentially an untested theory. Experiments follow that put the hypothesis to the test. Nowadays, there are a lot more rules around experiments than there were in Dr. Goldberger's time. For instance, you cannot take a group of prisoners and feed them a nutrient-poor diet, as it would violate ethical standards for scientific studies. Nevertheless, there are plenty of ways to conduct effective experiments within ethical bounds. After many experiments have been conducted, a hypothesis, if it has been consistently proven, it can then become a theory. Consider that everything you'll read in our nutrition textbook this semester is the result of enormous amounts of experiments. This can be something like the recommendations for how much vitamin C an adult needs, or the role that certain kinds of dietary fats play in the inflammatory response, which is part of the immune system. The scientific process is continuous, so sometimes what was once considered a well-regarded theory can change with new evidence. This happened, for instance, with changing recommendations on cholesterol. At one point, nutrition science was only aware of one type of cholesterol, and that cholesterol, when elevated, was considered a risk factor for heart disease. As research continued, we discovered that there are more than one type of cholesterol. In fact, one of these variations is heart healthy. In the textbook, the example is given where nutrition scientists observe that babies who are breastfed have lower rates of infection, asthma, and allergies compared to infants who are fed formula. They have a hypothesis that component X of breast milk is what creates these benefits. To test their hypothesis, they design an experiment where there is a treatment group and a control group. This experiment could be done on animals or humans. So let's say you have 1,000 people divided into two groups. 500 get component X, the treatment group, because they're getting the treatment, and 500 get no component X. This is the control group. So we've discussed control and treatment groups, and a few other things we have to discuss include the variables. So when conducting experiments, scientists always have to be out on the lookout for the impact of variables, which are factors that can change a study's outcome. So in the breast milk versus formula scenario, a variable might be that parents who are more likely to breastfeed are on average better educated and have more access to healthcare. So those are variables that can affect all sorts of health outcomes, including rates of infection. So a study that was looking at breast milk versus formula would have to account for the variables of education and healthcare access. So continuing to dive into some of the details of scientific experiments, there are two very basic kinds that we'll discuss here. Any experiment that uses living animals is in vivo. Vivo being Latin for life, or for those of you who speak Spanish, very similar to the verb vivir, to live. So in vivo, this could be animals or humans. The advantage with these experiments is that they are closer to real life, right? We want to find out how vitamins and minerals and different phytonutrients impact our bodies, right? In vitro studies, on the other hand, are those that are performed in laboratory settings. Sometimes these are called test tube experiments, though, of course, they can also happen in petri dishes or other sort of mediums one finds in laboratories. The advantage with these experiments is that they're inexpensive, simple, and they're really easy to control, so they have a lot less confounding variables. So if we were thinking of compound X in breast milk and why it might be that breastfed babies have lower rates of infection, we could do an in vitro study where we might put that compound X in a petri dish or test tube alongside some infectious agents and see if the compound X can neutralize or kill off the infection. This is a simpler test to do than in vivo tests. For instance, actually having babies and having to account for all the possible confounding factors that occur in real life. For instance, the varying environments that babies grow up in. Certainly some are exposed to more infectious agents than others. So in the bigger picture of scientific research, a typical progression is that studies begin in laboratories and then they progress to animal studies. If, for instance, the laboratory study shows that compound X shows promise in vitro, right? If it doesn't show promise, it probably never goes on to become an animal study because the animal studies are a bit more complex and expensive, right? And then so if it gets to that second level of animal studies, if compound X, for instance, shows promise in the animal studies, then it might be able to move on to human studies. So regardless of what type of study we're talking about, after any kind of experiment is over, the next step is interpreting the results. So in this example, we have a pretty clear-cut result. The experimental group, the experiment went on for 12 weeks, right? And as time passed and the intake of compound X increased over time, those receiving compound X in the experimental group were protected from infection at over 3 times higher a rate than those in the control group who received none of the compound. This study also points out the usefulness of doing longer-term studies, because you could imagine if this study was only 2 or 3 weeks long, the results would have been entirely different. Well, there are a lot more studies that are done in animals than humans due to the lower cost involved. Human studies are preferable when possible because animals have, of course, a really different biology than humans, different lifestyles and activity levels, and of course, very different diets and different digestive tracts as well. So, in the next few slides, we will look at some studies that are done on the most relevant of animals, which is us humans, right? There are several kinds of observational studies. What makes observational studies different is that there's no intervention. So there's no group of people that are being given compound X or 75 milligrams of vitamin C or being instructed to follow any kind of special diet. Scientists instead are simply collecting data and analyzing it. Data can be collected via surveys or actual physical examinations, which could involve collection of blood work, for instance, taking blood pressure, measuring heart rates, measuring waist circumference, height, and weight. A famous example of an epidemiological study is that of the Pima, a group of indigenous Americans whose traditional territory happens to span the US Mexican border, where Arizona meets Mexico. Researchers looked at health data from Mexican Pima and US Pima and found that the US Pima had higher weights and rates of diabetes. This is a famous epidemiological study because these two groups of Pima are genetically the same, but because they have spent the last century under different governments and with different influences, their diets and lifestyles have diverged. The US Pima began eating a more modern diet several generations ago, while the Mexican Pima continued with a more traditional diet. So many nutrition studies were influenced by this epidemiological study to look at the impact of modern diets on the rates of obesity and diabetes. One of the most important epidemiological studies in the country is the ongoing effort of the National Health and Nutrition Examination Survey, or as it's often called in shorthand in the nutrition field, NHANES. It's an ambitious, ongoing, decades long effort to understand and catalog what the health and diet of Americans looks like. Researchers for NHANES travel around the country in a near continuous journey in specially fitted RVs to assess the health of Americans. They go to every city, state, and county in the country. Most nutrition research involving humans is observational, involving either a case control study or a cohort study. In a case control study, individuals with a certain health condition are matched those who don't have that condition to try to assess what factors might be involved in that disease formation. For instance, matching those with diabetes type 2 to those who don't have the condition. Researchers then look for what are the differences in these two groups that might have an impact on the risk for developing diabetes type 2. In a cohort study, everybody is in the same group or cohort, and scientists analyze data to see if they can make associations between diet and lifestyle and the development or lack of development of a disease. These cohort studies can either be retrospective, meaning researchers are looking back over years, often decades of data, to identify current health outcomes and what is related to those, or they can be prospective cohort studies. Researchers start out with a group of initially healthy people and then follow them over time to see who develops what health conditions and who does not. In both cases, generally, the longer the period of time, the more valuable the study is, particularly when you think of chronic disease, which is a huge issue in the US and globally. So diseases like heart disease, kidney disease, diabetes, These diseases take decades to manifest, so long-term studies are what will give us interesting data to look at. So in this slide, we're just illustrating the points we were making on the previous slide, how the different types of studies have a different timeline. So the retrospective one, starting, for instance, 40 some years in the past and ending at the current or near current date, looking at the health data, how it relates to decades long information collected versus a study that begins at a current date with healthy people and then follows them over decades and then studies the health data at the conclusion. The textbook mentions a few classic examples of correlations. The first one is as a population's intake of sugar-sweetened beverages, think Coca-Cola, Gatorade, that kind of thing, as that increases, weight increases. This is called a positive correlation. Not positive as in good, but positive as in both variables are moving in the same direction, up. Sugar-sweetened beverage intake and weight. The second correlation discussed in the textbook is as fruit intake among a population declines, high blood pressure increases. So that is an inverse or negative correlation. One variable goes in one direction and another variable goes in the opposite direction. So here is a visual representation of what we discussed in the previous slide. You can see in the first correlation where you have sugar-sweetened beverage intake increasing and obesity increasing, the line graph moves up diagonally. So that's the positive correlation. And in the second graph, when we're looking at fruit intake amongst a population declining while high blood pressure increases, we're looking at a negative correlation, and you can see the graph moving diagonally in the opposite direction. So epidemiological studies have limitations, and just because there's a positive or a negative correlation, it doesn't mean that these two things are necessarily linked. In the previous example, we discussed things that, well, it's pretty logical to associate increases in sugar sweetened beverage intake with weight and lack of fruit, which has a lot of fiber, increasing blood pressure. There are also plenty of correlations you could find all over the place that don't end up being linked when further research is done. And the book mentions kind of a silly example, but lemonade drinking and ski accidents in Colorado, for instance, that people drink lemonade in the summer and there are very few ski accidents, and in the winter people drink very little lemonade and there are more skiing accidents. So lemonade isn't actually correlated, well, isn't actually causing any skiing accidents, or the lack of lemonade rather. It's just a coincidence that this is, when people drink it, it's when it's hot out and there's nobody skiing, right? So correlation is not causation, is the famous saying in science. Okay, so in the next few slides, we're going to take a look at human research with experimental studies. So actually taking groups of people and making some sort of change to an aspect of the diet, since we're talking about nutrition science here. We'll go into some details with a few examples here coming up. When researchers conduct experimental studies with humans, researchers will divide up groups of people into a treatment group, and a control group. So if we go back to that example of component X in breast milk, that um, the theory is that it can lower infection rates, right? So researchers could enroll formula-fed infants in a study and divide them into two groups. The experimental group would get the formula that has that component X in it, and the control group would get a formula that does not have component X in it, in order to evaluate these two groups to see if there are differences in the rates of an infection. And this could be over, 1 month, 2 month period, 6 months, a year, but generally the longer the period is, the more accurate it will be. So you could catch potentially more cases of infection or non-infection. When we think of the different kinds of research, each kind has its benefits and limitations. Some of the epidemiological studies we talked about earlier can be really valuable because they often involve thousands, if not hundreds of thousands, sometimes even millions of people. So you can really look at vast amounts of data and groups of people, and it's a tremendous amount of information. The randomized control trials are generally much smaller groups of people because they're pretty expensive to run these trials. Since they're randomized, that gets rid of the bias factor, but since they're relatively smaller amounts, groups of people, you have issues where there's going to be differences with many other factors, right? Genetics, lifestyle. So there are other potential confounding variables. But in general, RCTs are considered the gold standard in nutrition research. But of course, it takes a lot of different kinds of research in order to build up scientific knowledge. So a pragmatic trial is often considered kind of a next step in scientific research. If some behavior or nutrient is found to be beneficial, then it might make its way out into a trial where the general public gets to use this. This often happens with aid work, for instance, giving out vitamin A supplements in areas of the developing world where there's a great deal of vitamin A deficiency, and seeing, well, what's the impact of the vitamin A supplementation. The scientific process, of course, is not perfect, and human beings have flaws, they have biases, and not only that, a lot of research is funded by private sector interests. So going off the example we've talked about earlier that the textbook focuses on, for instance, the formula industry, the folks who make baby formula, for instance, Nestle is one company that comes to mind. They might not want to fund scientific investigations to find differences in health outcomes between formula-fed and breastfed infants, right? Because those studies generally show that breastfed infants do better, and that would hurt sales of formula. So we always have to look at sources of funding for studies and look at the bigger picture of what the trends are in scientific research over many years, and not necessarily just focus on the outcome of one particular study. So there's a big difference between what scientists find interesting and what the media finds interesting. So sometimes the most sensational claims are what the media likes to cover. So, for instance, the textbook mentions that a study might find that feeding mice curcumin, which is a spice, protects the animals from cancer. The press might then report that, hey, all you have to do is eat this curcumin and you'll be protected from cancer. Well, that's just one study showing possible benefits of one nutrient in mice, and that doesn't mean that it will automatically transfer to people the same way. But many times the kind of dull nutrition advice, for instance, uh, eating plenty of fiber a day protects against colon cancer, isn't what the media picks up on because it's not uh, sexy sounding. It doesn't make a big splash. Since the popular press reports nutrition news in a way that doesn't always tell the full story or really tell the story from front to beginning, kind of just snippets at different times. Um, Nutrition can really appear to be a confusing subject to people in the public. And I think one of the best parts about taking an introduction to nutrition course is that your instructor and your textbook, we have no other purpose other than to educate you on the science of nutrition. So we're not here to entertain you, although hopefully it's not too boring. And we're also not here to sell anything. So this is a pretty unbiased source of information. Speaking of unbiased sources of information, the government is also trying to act in the best interests of the population. Of course, it's in the government's interest to have a healthy and well-fed population. And as part of that, we have the Federal Trade Commission. So that's a federal government agency that protects against unfair and deceptive acts or practices by businesses in the US. And when companies make outrageous claims or have false ingredients in their products, or their products don't contain what they say they should contain, people can file complaints with the Federal Trade Commission, and they'll investigate, and they can give out fines and take action against companies that are involved in fraudulent practices. And well, the FTC acts on our behalf, and the government tries to promote good nutrition information and protect us from harmful information. We don't live in a country where the government is particularly aggressive about this, and you can imagine it would be incredibly expensive to chase down every source of false or misleading information out there. It's really up to us to be knowledgeable consumers of information, and also to be accepting of the fact that science involves accepting changes. What was true 20 or 30 years ago in science sometimes is still true. For instance, we'll talk about the 20 amino acids that make up proteins. That's still true. But some things that were true 20 or 30 years ago have shifted a bit over time as science has evolved and more research has been done. As a nutrition professor and someone who worked in public health in clinics for many years, people ask me all the time about, oh, such and such, doctor that they see on social media promoting this or that diet or supplement, and what do I think of it? And I always tell them to be a bit suspicious about the motivation of the person they're listening to. If they're selling a product or service, they're quite likely fairly biased, right? So it's really important to ask questions. What's the source of this information? Is it from a scientific journal, or is it from TikTok or Facebook or some social media thing where someone has a financial interest in promoting a certain product or diet or service? And of course, here you can count on the textbook. The textbook has no other ulterior motive. This is a really important section of the book. When you evaluate nutrition information, look for those red flags, like your mom told you when you were probably 6 or 7 years old, right? If it looks too good to be true, it almost always is. And uh, there's a lot of misinformation out there that is essentially marketing material, right? So no different than the ads for the toothpaste that will magically make your teeth super white, right? Um, Things in the nutrition and health world operate on the same level as that, or the car that if you buy it you'll appear beautiful and successful and it will never break and everything like that, right? You have to be a cautious consumer. At the end of chapter 2, there is a section about searching for information online for nutrition that's worth looking over. But I would just be very wary of where you look online for nutrition information. Sticking to government sources, USDA, of course, the Academy of Nutrition and Dietetics, organizations like the Center for Disease Control and Prevention, Food and Drug Administration. Those are going to be your best sources, and universities. For instance, Harvard Nutrition has a great newsletter they put out, and obviously, anything associated with big state university nutrition programs is usually going to be at least quality information and unbiased, or not having too much bias in it. I think of the health and nutrition apps on the same level as I think of anything online. There are some that can be useful, and there are some that have their own reasons for existing. They have some bias built in because they're selling certain products, services, supplements. So I would reserve the same degree of caution with those as with any other kind of nutrition information. So, just a key brief point to make here, that the U.S. National Library of Medicine and National Institutes of Health, the PubMed website, those are good places to look for scientific literature. And a couple times here, the book mentions it, and it's in the slideshow, the Academy of Nutrition and Dietetics. That's the parent organization of registered dietitians, which is the highest national license for nutritionists. So everyone who becomes a dietitian has a degree in nutrition from a nationally recognized program that's following kind of a universal curriculum, and then they do rotations in clinics and hospitals for a period of about, I think it's about 8 to 10 months. I did it, but it was 15 some years ago. Um, so that's a really trustworthy institution when it comes to nutrition, the Academy of Nutrition and Dietetics, and they have a great website. Well, I think these last couple slides more or less rehash the same messages about being cautious with the nutrition information you intake. And this slide is just another kind of review of those same concepts.